Woohoo. All right. So this PowerPoint is going through the steps for one-way independent ANOVA and SPSS. I think, I don't know, I haven't disclosed this to you guys yet, but these PowerPoints are new. I haven't done this for previous semesters. Usually it was just a video and then they had to like go back and watch the video. So when you're doing your activities, I highly recommend going back to these because if you haven't been doing that already, because all of the interpretations are written out. It's pretty much a plug and chug of variables after you understand what your research scenario is. So these are good examples for you guys to cross-reference when you start doing, especially the tasks in the activity, the ones you have to do on your own. Highly recommend. Anyways, for the example I'm going through in this PowerPoint, we have a researcher who wants to know if a person's level of physical activity affects their ability to cope with stress in the workplace. Not a specific like kinesiology type example, but this is the one that I had on the Laird Statistics website. So that's where I get all of my screenshots from. But the way that they set up this study is that they had a random sample of 31 subjects categorized into 4 groups based on the number of minutes of physical activity they performed. So this is, I can't remember. I think it was in discussion 4 and 6. Some of you guys had methods where you were like, ooh, I'm gonna measure like level of physical activity as an example. I'm gonna measure that and use it as my independent variable, but you hadn't specified the groupings. It's totally fine to take a measurement and then group people based on criteria. So you can start with a ratio variable, but end up with a nominal variable because of the criteria that you select. So for example, we take 31 people, ask them how many minutes per week do you exercise? And then people who are sedentary would maybe be like, no minutes of activity, so 0. That would be our criteria for that group. And then low physical activity maybe is 30 minutes to an hour. Moderate might be between or greater than 1 hour, but less than 3 hours. And maybe high physical activity would be greater than 3 hours. I don't know. It's up to the researcher to decide the criteria. Sometimes maybe it's ACSM guidelines, or you might have some information from other lit reviews, but that's an acceptable way to create groups through actually taking a measurement or surveying people. You just have to specify. So for example, like you guys are going to be making like a research example for a 1 or 2-way ANOVA for your discussion this week. You can still take a measurement. You just have to make sure you specify how you're dividing your groups up. So this is how this particular example divided people: sedentary, low physical activity, moderate physical activity, and high physical activity. And then we measured the ability to cope with workplace stress using a questionnaire. And then from that questionnaire, a score was calculated. Higher scores indicated a person had a better ability to cope with workplace related stress. So in this example, our independent variable is the level of physical activity, because that's the nominal variable that's broken down into groups. Dependent variable is ability to cope with stress. When we put this into SPSS, very similar to our independent t-tests, we have to make sure that our grouping variable, our independent variable, gets changed to nominal. And then the default should be scale for the dependent variable, but just in case, change it to scale. And then we also have to indicate what our levels mean by means of using the values column in the variable view. So under values, we would say 1 is sedentary, 2 low, 3 moderate, 4 high. Okay. Once we set up our data, we can then start the procedures for actually running the test. For our examples in this class, you're going to assume that you have normal distribution and no significant outliers for each of your groups for the dependent variable measure. So that's not an assumption that you have to check for using the explore analysis. So just skip over that. The first thing we'll do in SPSS is set up the test. The assumptions are included in the output, so we'll check our assumptions after we get our test run, interpret the ANOVA results. If you have significant ANOVA results, then you look at your pairwise comparisons, and then we'll also go through how to calculate n effect size. So that we'll keep coming back to this slide, but the first thing we're doing is we're just going to go through the steps on how to set up the test. So in SPSS, once we have our data organized, we would go to Analyze, Compare Means, One-Way ANOVA. Okay, assume, again, one-way ANOVA is a one-way independent ANOVA. The process you would use for a one-way repeated measures ANOVA is different. So this is specifically for independent or between subject measures. Once you click in that, it'll bring up your variables in the left-hand box, and then you can sort them as your dependent variable and your factor or your grouping variable, respectively. Then we would make sure that we set up our calculations. So the options button in that main dialog box will bring up another dialog box that shows the descriptive statistics, homogeneity of variance test, and then Welch's test. So descriptive statistics will be like your means and standard deviations. Homogeneity will be Levine's test, so you can check your assumption. And then the Welch's test is going to be there in case you violate homogeneity of variance. Okay, so make sure those three boxes are checked. That'll take you back to the ANOVA dialog box. You'll click on the post hoc button, and that's where you set up your pairwise comparisons or your post hoc tests. For our class, we're going to use Tukey's post hoc tests. That's kind of one of the most common ones that you'll see. The selection of post hoc tests is often determined by how conservative or liberal the test is, which is related to how much error can be calculated into, or the different types of adjustments that go on in like the inner workings of the software. So Tukey's test is a common one. We're just going to use that one for our class. And this is when we have equal variances assumed. So there's multiple layers to the output. You first check your assumption to see which ANOVA table to read, ANOVA test or Welch's test. And then you also have to determine if you've met or assumed homogeneity variance to figure out what post hocs to read. So when we have equal variances assumed, we'll look at Tukey's results. If we do not have equal variances assumed, then we look at the Games-Howell adjustment. So once you have your post hoc set up, you click continue, and then OK, that will generate the output. So our setup is complete. Now we look at assumptions. Okay, so the actual output itself is gonna, it'll have a list of components in it. We're going to skip straight to the test of homogeneity of variances, because you always have to make sure you've met your assumptions before you can accept the results of your test. So this, different from a t-test, Levine's test is separated from the main from like the main ANOVA table. So we can see in this example, our p-value is in the sig column. Again, the null hypothesis for Levine's test or for homogeneity of variance is that we have equal variances between our groups, or the variance of each sample is the same. Our p-value in this case is 0.12, which is greater than 0.05, so that means we can accept our null. And then we can say there are equal levels of variances, or equal variances between our levels of activity. Okay. So we've met, in this case, our we have equal variances assumed or we've met our homogeneity of variance assumption. So assumptions have been checked. Now we can look at the ANOVA results. I have 2 slides in this section just to account for what would happen in either case. The first slide goes over if you've met homogeneity of variance, which is the case for this example. We would go straight to the ANOVA table where we can still see there's a p-value listed in the sig column for the F statistic. Okay. The null hypothesis for this particular scenario is that activity level has no significant effect on one's ability to cope with stress. Our p-value is going to be less than 0.001, which tells us to reject the null. So we can argue that activity levels have a significant effect on ability to cope with stress. We could also write this as there's at least one significant difference between activity levels and one's ability to cope with stress. So different ways we can interpret this, but all kind of pointing to the same idea that activity level has no effect on coping with stress. Okay. So this is if we met a homogeneity variance, which we did for our example. If for some reason, let's say for this example, we did not meet homogeneity variance and we violated it, then we would go to the Welch's test for the main effect, or for the p-value for the main effect. In this case, it's still less than 0.001. So our interpretation would be the same as what we had in our previous slide. Your p-value for Welch's test and for the ANOVA table will not always be the same. There are some instances like this one. I think also one of the practice sample data sets that I gave you guys in your activity, the same thing is true for that example as well. But the p-values when you record them, like for the exam or for quizzes or for like the tasks, if they don't match the p-value exactly as it is for the whatever table you're supposed to read, then it's considered wrong. So just keep your table straight, right? Whether you've met homogeneity of variance or whether you have not, that determines which p-value you read. And that would be assessing the main effect of our ANOVA. If we have significant differences, if we have significant results for our main effect, that's when we do post hoc tests. That is the case for this example, right? We had a p-value less than 0.001 from the ANOVA table. So then we can go down to our multiple comparisons table, and you'll see there's a division of Tukey's test and a division of the Games-Hell test. Now we said, if we have equal variances assumed, we read the Tukey's post hoc tests. If we do not have equal variances assumed, we would read the Games-Hell test. Okay. For our example, we met homogeneity of variance. Therefore, we read the ANOVA table. Therefore, we will read the Tukey part of the table, which I will just separate out here. So what this does is it gives you all of the different possible pairs between all of your variables. There are redundancies in the table, which is what is highlighted here. So oftentimes I ask you guys in the activity, list the significant pairs. And in previous semesters, I'll have people who put sedentary and low and sedentary. Like those are, that's the same comparison. It's the same variables. And you can see in the table that the p-value is exactly the same. The mean difference is also exactly the same. The only difference in the calculation is this mean difference is sedentary minus low, and this one is low minus sedentary. So this indicates that people who have low physical activity have a higher ability to cope with stress because the value is positive here, but it's negative here. Okay. So redundancies in the table, you only need to list the pair one time. But we can see from this example that from our p-value column, our significant pairs are between the sedentary and moderate groups, as well as the sedentary and the high groups, right? And where I'm getting that from is the p-values are below 0.05 for each of those comparisons, right? Again, redundancies in the table. But all of the other p-values in this column are greater than 0.05, therefore they are not significant pairs. Okay, so the way that we could write this interpretation is that being sedentary causes a significantly different ability to cope with stress compared to both moderate and high levels of physical activity. Okay. All right. After we have checked our post hocs, that's kind of the end of the ANOVA analysis. Okay. Then we can calculate the effect size. Now you'll note in the pre-recorded video, I recorded the lecture videos before I recorded the activity videos, and I actually found in version 27 they include a calculation of effect size, which is not what was true for previous versions that I've used in this class before. So we're going to still calculate the effect size, and then we can cross-reference it in SPSS similar to how we did for t-tests. But the effect size that we're calculating for one-way ANOVAs is omega squared. And we use information from the ANOVA table to help us with the calculation. So all of these have been labeled with their respective coefficients as you would use them to plug and chug into the omega squared formula. Hello, Nori. The interpretations of the effect size are different than Cohen's D. So I've given you guys the table here. If you have effect sizes with omega squared of 0.1 or lower, or kind of close to 0.01, that would be considered a small effect size. Around 0.06 would be considered a medium effect size. And then anything 0.14, close to 0.14 or larger would be large effect sizes. For this example, when we plug and chug our values into the equation, we end up with an omega squared of 0.416, which compared to our table values, that would be considered a relatively large difference between the means of our groups. We only get an effect size for the ANOVA as a whole, so this is really just showing us what is the difference, or kind of what are the group differences, the numerators between groups. So what are the between group differences, or what's the size of the between group differences for all of the possible comparisons in our ANOVA, which we end up getting as a large effect size. Okay. All right, questions on one-way ANOVA analyses so far?
So this one is not straight up 0 to 1. It differs because 1.6, 0.06, and then 0.14.
Yeah. So the way that there's different calculations for different types of effect sizes, and a lot of times you'll choose the effect size equation based on how you want to calculate your difference, or there's different like factors that go into what each effect size means. So like Cohen's D effect size is what we used for our t-tests, which has a certain set of like standard interpretations based off of the possible values you can get out of it. The same thing would be for omega squared. So they're just different guidelines, but essentially we interpret the guidelines the same way. So like if you had like an effect size of 0.03, that's closer to a small effect size than it would be to a larger one. It's still kind of on the subjective side, so I usually kind of grade those on the looser end, but for the most part, the examples in our class are fairly clean cut. Question in the chat, For the last slide, the interpretation would be for the main effect, correct? Because this would be coming from the main ANOVA table. So the effect size for the difference between activity levels is considered large, if that helps.
So this 1.9 is large because it's greater than 1.4.
Exactly,
4.14.
yeah. Mm-hmm.
So 1 to 5 is small, 6 to 10 medium, and
yeah, roughly. Yeah. All right. I'm gonna do a new share. Sorry, this cat is very needy. It's also dinner time, so she's probably upset that I'm still talking to you guys. Let me pull up the last one. Share. There we go. Okay. So the last test, two-way independent ANOVA. Our example for this one is, come on, PowerPoint. There we go. We have a researcher wants to determine if the effect of education level on interest in politics is different between males and females. So from this example, I've identified independent variable A, or what I've referred to as independent variable A, which is education level. Independent variable B would be sex or gender. And then interest in politics is the actual measure that we have collected from people. So for methods, we have 60 participants, 30 males, 30 females. They were randomly sampled and equally split by level of education. School, in this example, is referring to high school. College is like a 2-year associate's degree, so like community college, and then university is considered like a 4-year university or a 4-year degree. And then because they're equally split, we have 10 people per group. So if you want to think about it this way, group 1 is 10 people who might be females with a high school education. Another group of 10 females with a college education, females with a university education, males with a high school, males with 2-year college, males with 4-year college. So technically 6 groups in total, or yes, 6 groups in total, 3 for each level of university, 2 sets for males versus females. To figure out what political interest was, they used a scale, which provided a score. Higher scores indicated greater interest in politics. So this is generally how I'll present information to you guys for two-way ANOVAs. And just to give you an example of what we would call the test or different naming conventions that we could use. Independent variable A, we said, was education. This splits into 3 levels. Independent variable B, we said, was sex, which splits into 2 levels. And if you'll recall from the lecture video, or the first lecture PowerPoint, we said there's 2 main components that have to be included in the naming convention. The first is the number of independent variables. So we could either call this a 2-way or a 3x2 from indications of the number of levels that we have for each variable. And then we also need to include the type of samples that we've used. So we could refer to this as between, or independent for this type of ANOVA. Right? So the 4 different naming possibilities that I came up with are as follows, and any of those would be acceptable. Like on the exam, I ask you guys, what's independent variable, what's dependent variable, what type of test would you run? Any of these would be acceptable for a 2-way independent ANOVA. If you want to stick with 2-way independent, that's fine. Some people like to do the between because it helps them sort out the differences between the other types of factorial ANOVAs, but that's an example you can use. Similar to our one-way ANOVA, we have to organize our data such that our independent variables are listed as nominal, and we set the values for each of these. Some of you might be asking why, or you might be thinking education level is an ordinal variable. Because I think in the beginning of the semester, I gave you guys an example of like grade level, and it was ordinal, right? Because there's a sequence of the categories. So like if someone's in first grade versus second grade versus third grade, there's a sequence to how you proceed through the grades, but there's no discrete value on how each of those grades are different from each other. So I think the Laird statistics actually listed this variable as ordinal, and I just changed it to nominal so that we have simple examples that are consistent. You guys can just say for all of our ANOVAs that you have a nominal type of independent variable. The test does work if you also have an ordinal variable, but keep things simple. Okay. So once we set up our data, we then have our task list to set up our tests. Again, assuming we have normal distribution and no significant outliers for our dependent variable for each possible group that we've measured. So to get to a two-way ANOVA analysis, we go to Analyze, General Linear Model, and then Univariate. Okay. Univariate just means you have a single dependent variable. If we had a MANOVA, which is a multiple analysis of variance, that's when we have multiple variable or multiple dependent variables, we would use a multivariate test. We don't do examples of that in this class, so univariate is going to be what you're going to use for two-way independent ANOVAs, and then for all of your repeated measures ANOVAs, that's where they are located. If you're like, ooh, I wonder, forecasting into the future, that's what we're doing next week. Okay, but Analyze, General Linear Model, Univariate. That will bring up your variable selection dialog box, and you can sort your dependent variable accordingly, and then your independent variables will go into your fixed factors box. You then can see we have several options on the side. We're not going to use all of them. To set up our post-hoc / pairwise comparisons, I'm going to actually go back one slide. You can see there's a post-hoc button and there's an EM means button. EM stands for estimated marginal means. We're going to use this to set up our post-hoc tests. The actual post-hoc setup in here is kind of weird for two-way ANOVAs, so we're not gonna use that one. So we'll go EM means. We'll set up our post-hoc tests. You'll insert all of your variables into this box that says display means for. So we can see a main effect for gender, a main effect for education level, and then the interaction effect is kind of notated with an asterisk. It's kind of small, but it is there. You'll check the box that says compare main effects, and then we're going to use a Bonferroni adjustment for our pairwise comparisons for this test. Then you click continue. That'll take you back to the ANOVA dialog box. In your column of potential buttons, you'll click the options button. This will allow you to choose certain calculations that you want to include in your output. So we'll do descriptive statistics, estimates of effect size, and homogeneity tests. Click continue. And then at the bottom of our ANOVA dialog box, we're going to click the paste button, but I'll just show you where it is. It's down here. Okay, so we've done estimated marginal means, options, paste. The paste button is going to bring up a new data window we haven't worked with yet. That's called a syntax window. So up to date, we've done a data window, which is where you put all of your data. your output window, where you get your output, and the syntax, which is a lovely place for the coding that goes into the analysis in the software. When the syntax pops up, you're going to see an EM means row for your pairwise comparisons for each of your independent variables. And then you'll see another row for your interaction, but it won't have this compare part down here. We actually have to add that in for both of our interactions, so that way we can look at what are known as simple main effects. So that's where we're looking at the comparison of gender within education levels, and then we're also looking at the comparison of education levels within gender. So I show you guys actually how to do this in the activity, so we won't spend too much time on it here. But once you set up the syntax, you then go to the Run tab and then click All, and that will run the log or the new syntax for the test to generate your output. So once we've set up the test, we can then check our assumptions, which is in SPSS, Levine's test for homogeneity of variance. It'll show up as this kind of complex table. The one you're going to focus on is the p-value for the row that says based on mean. So our p-value in this instance is 0.061, which is larger than 0.05. So we can say that we have equal variances between groups for both sexes and education levels. Or equal variances between all groups is also acceptable. If you have violated homogeneity of variance, you'll recall from the lecture PowerPoint, we said, oh no, you'd have to check sample size if your sample sizes are equal, if they're large enough, and then kind of the ratio between the largest variance and the smallest variance. We're not going to do that in this class. So kind of just note, if you violated it, say, oh no, homogeneity variance is violated, and then just continue with your analysis process. So now assumptions have been checked, then we can look at the main effects of the ANOVA. So again, 3 main effects for a 2-way ANOVA: main effect of sex, main effect of education level, and then the interaction effect between the two. So we'll start with the main effect of independent variable A, which in this case I argued was education level. And I did this in the recorded video too. I mixed them up because the way that I named them, they were listed as opposites in SPSS, which is dumb. But so independent variable A in our scenario is education level. In our main ANOVA table, it'll show up as the test of between subjects effects. That's what the table is called in your output. You'll see the main effect for gender, main effect for education level, and then the interaction effect and their respective p-values. I've just highlighted the main effect for education level, and the p-value for the main effect is less than 0.001. So we would reject the null hypothesis and say there is at least one significant difference between education levels regardless of a person's sex or gender. Okay. So make a mental note, since we have a significant effect for education level, we would then need to look at the post hoc test to figure out which education levels are different from each other. So that takes care of our first main effect. The p-value for main effect of independent variable B would be our next concern, which is gender. So p-value in this case is 0.448, which is larger than 0.05, right? So we would accept the null and say that gender has no significant effect on political interest, regardless of education. So it doesn't matter what type of education level you are, there's no difference between genders. Males and females generally have the same level of political interest. Okay. So since there is no significant main effect, we don't need to look at post hocs for gender. The last p-value we look at in that table is the interaction effect, which is between gender and education level. I just saw chat. Can you expand on your question, Husam?
I mean, according to up to here, it's like the question is saying the political party. So up to this point, we are still assuming that there is no difference, like
Correct.
in political views.
Yeah, based on the output. So far, gender has no effect on political interest, but education level does.
So we are collecting the data on education level right now, up to here.
No, so we have a combination of everything. So we have political interest scores for males and females at each level of education. The first one here says, like, regardless of education level, are there differences between males and females? And this p-value says no significant difference between the means. So we would say males and females are not significantly different on their political interests. For education level, that's saying, are there differences between a high school education, a 2-year college education, or a 4-year college education on political interest? And based on this p-value, it's suggesting there is a significant difference. But it's saying there's at least one significant difference. So we would have to look at the post hoc test for that one.
Okay.
Yeah. And then we would look at the interaction effect, which is the last one, which is saying if we look at gender within education level, or if we look at education level within gender, are there significant differences? And based on this p-value, 0.002 is less than 0.05. Therefore, we would say there's a significant interaction between sex and education level. And whenever we have significant p-values in this table, we look at post hocs for those particular main effects. So in this case, I've highlighted on my checklist. Now that we've looked at all of our main effects, we noted that our education level was significant and our interaction was significant. So our pairwise comparisons, there's always going to be 4 options, one for independent variable A, one for independent variable B, and then there will be 2 comparisons for the interaction effect, because we either look at A within B or B within A. So that's why I've highlighted these particular ones here, because for the example, those were the ones that had significant p-values. And for the pairwise comparisons for A, we would have a table that looks like this. So this is similar to like the post hoc test you would see in a one-way ANOVA, where we've got all of the possible pairs of our levels of education. Again, there are redundancies in the table, so you only list each pair one time. In this case, all of our pairs are significant. So as far as like when I ask you guys list the significant pairs, it would be acceptable in a case like this to just say all of the pairs are significant. Or you could say, as an interpretation, there are significant differences between all pairs of education level, regardless of sex, right? Specifically for political interest. So I guess I could have added that. There are significant differences in political interest between all pairs of education levels, regardless of sex. Okay. I also put another note here. You only look at it if there's a significant main effect. Because I always have some students every semester who just decide to go crazy with the post hocs and then they list all of them, even if there were no significant main effects. So don't do that. Only post hocs if you have a significant main effect. Okay, so that takes care of our main effect for education level. Then we can look at the pairwise comparisons for our interaction effect. We'll do kind of 2 steps for this one. The first, we'll look at differences between education levels within each gender. Okay, so if you're looking or referring back to the syntax that you typed in, this would be the compare education level line of code that you wrote. So for here, we've got our column of p-values. And if we evaluate all of those p-values, they're all less than 0.05. So a similar instance to our main effect of our education level, we can say all pairs are significant. Okay. And the way that we can interpret this is that there are significant differences in political interest between all pairs of education level for both males and females. Okay, so if we used one example here, high school education is significantly different from a 2-year college education within male participants. So if you were listing interpretations of each individual comparison, that would be an example. That takes care of the first way we can look at the interaction. The second way would be the reverse of that. So looking at differences between males and females within each level. So this would be associated with the compare gender line of code that you stuck into the syntax. And for this one, if we look at our p-values, we can see that the only significant difference is between males and females at the university level, which is likely why we didn't have a significant main effect for gender, right? Because at other levels, they're not too different from each other. So interpretation here would be there's a significant difference in political interest between males and females with a university education. And that's it. Okay, so it's a very stepwise process, right? We do set your test up, check your assumptions, interpret your ANOVA results accordingly, listing your 3 main effects. If any of those main effects is significant, post hoc tests. And then you list your significant pairs from your post hoc tests. After that, you can calculate your effect size, which technically you're not doing any calculations for 2A ANOVAs because SPSS will do it for you. Also, it's a little bit more of a complicated equation, so I just don't include it in the semester. But for a 1-way ANOVA, we did omega squared. For a 2-way ANOVA, the effect size that SPSS automatically calculates is the partial eta squared, which is this N looking symbol, Greek letter. The interpretations of omega squared and eta squared are exactly the same. So like the guidelines that you use for the values, same between either one, which makes it nice and easy. But the way that we look at effect sizes for the independent variables, or the main effects of the independent variables, we take them directly from the test of between subject effects table. Okay, so for this example, gender or sex had an effect size of 0.01, which is relatively small. Education level had an effect size of 0.879, which we would say is large. Pretty easy to kind of disseminate out, okay? Now, for the interaction effect, partial eta squared is going to be a little bit different. So it gives you have a partial eta squared on the main ANOVA table, but don't read that one, okay? Where we're going to go is actually in the univariate tests in the output. So the way the output is organized is you get all of your main effect results first, and then at the bottom of the output, you have all of your pairwise comparisons. So within each pairwise comparison for each independent variable, and then for each of your interaction effects, you're going to have this univariate test box. and that will split up your comparisons. So for this one, I got this test from the compare education level within sex or gender. So my partial age of square is listed over here. And the way that we can interpret this for the male row, we had an effect size of 0.83. So that means we had a large effect size for differences between education levels in males. Because this came from when we were comparing education levels within each gender. Similarly, for females, also a large effect size based on the value, right? And we could say there was a large effect size for differences between education levels in females. Flip side to that, if we went to comparison of genders within school, we get a univariate test box that has our p-values listed on the side. And then we would have similar ways to interpret each of those effect sizes as we did in our previous examples. So for high school, we had a relatively small effect size for differences between males and females in that school level of our education. College would be also considered small, and then our university value would be considered large. And that's all I have for today. But perfect timing. It is 5:50. Are there any questions? Okay, cool. I'm sure there will be questions. I feel like the ANOVAs, you get a better grasp on what you're supposed to do and when you're supposed to do it when you actually have an example to work with. So the activities will be really helpful. So once you go through those, feel free to reference the PowerPoints for the steps. But if you have any questions as you go through your activities, shoot me an email. I can help you go through everything. And I guess that is it for today. So I'll stop